Hi everyone, in this video we are going to discuss the energy of electromagnetic radiation, but specifically of the UV or the ultraviolet radiation. So before we do that, let's review the electromagnetic spectrum. So at the highest end, so the high energy, we start off with gamma rays. So gamma are much higher energy than X-rays, which are higher than ultraviolet, higher than visible, higher than IR or infrared, which are higher than your micro, which are higher than your radio. So remember, radio is your low energy, all the L's go together. So low energy, long wavelength, low frequency, which means on the other end for gamma rays, they have short wavelengths, okay? And then they have high frequencies. But this needs to be very clear in your head already. But what we're going to do in this video is talk about this, but more specifically ultraviolet radiation. So these three that I just underlined are all the type of electromagnetic radiation that comes from the sun. But ultraviolet or the UV radiation is the most dangerous for us because out of these three, it is the highest in energy. Again, just in comparison to visible and IR. Obviously, X-ray and gamma are even higher in energy. So let's talk about UV radiation. But in order to do that, we need to kind of introduce a new way of drawing a molecule. So when I draw a big circle like this, I'm just saying there's one atom, and then I'm going to draw a bond. But with these bonds, I'm going to draw them in terms of springs. And so, and then here's another atom. And then we're going to draw another spring, and then we have another atom. So in this picture, I have two bonds. Here's one, here's another, and then I have three atoms. So here's one, we'll just put a positive because nucleus is positive, and then 2 and 3. So from here, what we want to think about is what happens when UV radiation comes in and hits a bond. So when ultraviolet radiation hits a bond, what happens? And the answer is actually really cool because it's three different things. So we could have one, which would be our low energy, and so for low energy for UV, it actually has a very specific range. It is 320 to 400 nanometers. This is also referred to as UVA energy or radiation. In the middle, we have kind of middle energy and somewhere in the middle, and this has a range of 280 to 320 nanometers. This also has a specific name. These are considered UVB rays. And then the last one is high energy. So we can actually get really high energy from ultraviolet radiation, and this has a range of 200 to 280 nanometers. So remember, the smaller the wavelength, the higher the energy. And this is considered UVC radiation. So what I want to do now is look at this molecule that we just drew up here with the little springs for the bonds in terms of UVA, UVB, and UVC radiation. So let's start off with low energy. So when something with low energy hits a bond, so we're going to keep this one the same regardless. This is the bond we're going to talk about. So when it hits with low energy, basically what happens is your bond is going to wiggle, okay? So it wiggles, nothing fancy happens, doesn't really damage the molecule, doesn't break it apart, doesn't remove any species. It just basically makes it kind of wiggle. And so we just draw it in a funky, like spring-like way. Okay, nothing too dangerous. But let's see what happens when we increase the intensity or we increase the amount of energy. And so now we're going to talk about what happens to this molecule when UVB radiation hits it. So we have one atom, here's the spring, nothing fancy happens. Okay, so now when UVB hits this bond, the one that's next, what happens is the spring stays the same, the bond doesn't do anything different except for the fact now that this energy has come in, it actually ejects an electron. So remember, an electron is a negatively charged particle. So if a negatively charged particle is removed from a bond, what that means is it leaves a positively charged species behind. This is no good. Think about what would happen inside your body if this radiation hits the bond and then it removes an electron and leaves a positively charged species in your body. That means this molecule is now going to run around your body and do anything it possibly can to find an electron. It wants to react, it wants to come back to neutral, it hates being positive. That means that when this happens inside of your body, you have genetic defects. This is bad news. This is really bad news. You do not want to have that. And what you should be thinking, and we'll get into this in a different a different video, is this really is going to cause skin cancer. So it's bad news. We need to protect ourselves from UVB radiation. Now, let's move on to even higher energy. So UVC radiation. So when UVC radiation hits this bond, what ends up happening is it breaks. Okay, so you actually see a break in the bond. We remove the bond, so now this atom is all by itself, and these two atoms are only attached to each other. This is bad, okay? So it breaks your bond, okay? Immediately, I think cancer, okay? This would be so bad if our body were hit with UVC radiation. So let me ask you a quick question, see if we're all on the same page. Which form of UV radiation, and I keep saying UV, but please know it's ultraviolet radiation, is the most damaging? Only 3 options, A, B, or C. Go. Did we get an answer? Hopefully we did, because we just talked about it, but the form of UV radiation that is the most damaging is UVC, because it is the highest energy. Highest energy is bad. Keep thinking that. High energy is bad. Here is the thing. We should be so incredibly grateful because oxygen and ozone actually absorb most of our UVC radiation, and they protect us. And so we are not constantly being bombarded with UVC rays. UVB is our real danger here on Earth. But let's talk about this first part, the oxygen and ozone protecting us from UVC. So let's just draw out a little chart here. We're going to start with 200. We're going to go to 280. We're going to end at 320. So these are our nanometers. So we just discussed this at 200 to 280. That is our high energy. That's our UVC radiation. 280 to 320, that's a little bit lower in energy, but still pretty nasty. That's our UVB radiation. So what we need to be thinking about here is, how does oxygen and ozone protect us? So oxygen is a diatomic. It's doubly bonded. I fully expect you to be able to draw this out by now. So it's doubly bonded, and what's really cool is when we take oxygen and we hit it with UV radiation, specifically with a wavelength that is less than or equal to 242 nanometers, the double bond splits. So the entire energy goes right into this double bond, forcing it to break apart, and you're left with 2 monatomic oxygen atoms. So they used to be connected. The UV hits, or the UVC essentially radiation hits the bond. It breaks apart, and now you have an oxygen over here and an oxygen over here. When that happens, it essentially absorbs that energy, so the UVC radiation is no longer penetrating down through the atmosphere to hit us as humans. So thank you, oxygen. You are my new favorite molecule for right now. Okay, so that oxygen protects us from the UVC radiation. So that goes from 200, okay, to about 242. Oxygen protects us from this section. However, we have this whole other group over here with 320 all the way to 242, where we as humans are left vulnerable. And that is where ozone saves the day. So ozone, remember, has 3 different atoms in it. We say that one is doubly bonded to one oxygen and one is a single bond to another oxygen. Now we know that this exhibits resonance. And because this exhibits resonance, we know that instead of saying that one of these is always a double bond and one of these is always a single bond, actually these bond lengths are somewhere in between. So we could actually consider them somewhere between a single and a double bond. This just means that the bonds in ozone are significantly weaker than the bonds in oxygen. So now for strength, single bond is weaker than a double bond, which is weaker than a triple bond. Okay, triple bond is the strongest one. So oxygen is the strongest one. So the problem is, when we have wavelengths that are greater than 242, it's not enough energy to break that double bond of oxygen. But it's enough energy to break the single/double bond, so there's somewhere in between the 1.5 bond of ozone. So what we have here is ozone. And when it's hit by UV light with a wavelength less than or equal to 320 nanometers, it breaks apart into diatomic oxygen and monatomic oxygen. So thank you so much, ozone. Ozone actually then protects us from this section here of 242 all the way to 320. And it simply is because the bonds of ozone are weaker than the bonds in oxygen. So these lower energy radiation pieces can actually break the bonds of ozone. They absorb that energy and essentially block that energy of coming down all the way to us on Earth. So we're going to end this video of just saying thank you, oxygen and ozone. We love you. Have a great week, guys.